In this video, we're going to review what you know about finding the inverse of functions, but we're going to take it a little bit further by talking about restricting the domain of functions as well. So just as a refresher, there's three ways that you can find the inverse of something. If you're given a function as just a bunch of ordered pairs like a table, all you have to do is switch the x and the y coordinates. So just to test that, I plugged some points into Desmos, and you can see here the point 1, 2 became the point 2, 1, and 3, 5 became 5, 3. In other words, on the graph you can see this point became this point, which means these are all reflecting over this dotted line here, which is the line y equals x. And that's exactly what it says here for number 2. For on a graph, you can just reflect the graph over the line y equals x, and that will be the inverse. Up here though it says in order to do this algebraically, you'll have to do step 3, which is interchanging x and y and then solving for y. Now I did say we'd have to restrict the domain of some functions, and the reason for that is if you look at this example here on Desmos, let's look at the original green function first. If I were to draw a horizontal line through this, there's a point where the horizontal line would cross through the function twice. That means it fails something called the horizontal line test. You may have heard of something called the vertical line test before, and look at the inverse here, or the red graph. There's a point here where I could draw a vertical line through it, and it would fail the vertical line test. So that's pretty important. So we could say if a function fails the horizontal line test, its inverse isn't a function. Even though the original green graph here was a function, it does pass the vertical line test. The inverse was not a function. So let's try a couple examples. For number 1, I'll switch f of x to say y, and then I'm going to switch x and y, and then solve for y. That means I'll have to add 2 to both sides, and then divide both sides by 3. If you think of what the original function does, it takes some input x, multiplies it by 3, and then subtracts 2. And if you look at the inverse, so f inverse of x, it takes some input, adds 2 to it, and then divides by 3. So you can see how f inverse of x is undoing everything that f of x does. When you graph both functions, you can see they're both linear, and the domain and range of both of them are all real numbers. And you can see how they're reflecting over that line y equals x again. Since the domain and range is all real numbers for both functions, I don't have to worry about restricting any domain. Number 2 is a cubic function, but again, if I switch x and y and solve for y, I'd have to add 5 to both sides, then I would multiply by 2 to make the 1/2 go away, and careful on the left side because multiplying by 2 means you have to distribute the 2 into both things. And then just take the cube root of both sides to make the third power go away. And the third root isn't the same thing as the square root, so I don't have to put a plus or minus in front. And if you graph both functions, again, you can see the reason for that is because the domain and range for both of these is the same. They're both all real numbers. So I still don't have to worry about restricting any domains. But now let's look at the function f of x equals x squared. So we'll do this algebraically again, so I'm going to switch x and y and solve for y, which means I'm going to have to take the square root of both sides. And when you're the one taking the square root of something in a problem, you have to put a plus or minus in front of it. So this would be plus or minus the square root of x equals y. And if I graph that, that's basically just the positive and negative square root graph, which is at 0, 0, and then 1, 1, 4, 2, that's the positive side. The negative side would be 0, 0, 1, negative 1, and then 4, negative 2. And remember, you can always make an xy table if you're unfamiliar with a function's graph. But there's a problem with this because it doesn't pass the vertical line test. Basically, everywhere it exists, it doesn't pass the vertical line test. And if we think back to the original function f of x squared is just a parabola that looks like this. And thinking back to the beginning of the video, this doesn't pass the horizontal line test. So let's go back and restrict the domain of the original function so that its inverse is a function. Basically, I have two options. I just have to cut this parabola in half so that anywhere I draw a horizontal line, it's only going through one side of it. So if I cut a line right down the middle, I'm either going to be keeping the left half where the x values are less than or equal to x, or the right half where the x values are greater than or equal to x. And that's going to change what we get for the inverse. So if I were to keep the left half here, if you think of reflecting that over the line y equals x, that would give me the bottom half of the square root graph. That means f inverse of x would be the negative square root of x. So if I just cut the right side of the parabola, that would be like keeping the top side of the square root graph. So that would be f inverse of x equals the positive square root of x. So depending on how I restrict the domain, the inverse will change. Let's try that with another example. Here it says find the inverse of the function f of x equals x plus 3 squared. This is a pretty simple function, so you could actually think of this just in steps. Like this function takes an input and adds 3 to it, and then squares that. So if I wanted to write an inverse function that undoes this, I would want something that first takes the square root of it and then subtracts 3. So I'll write the square root of x and then minus 3. Notice how the 3 isn't inside the square root because this would be taking x minus 3 and then square rooting it. So this function takes the square root of x and then subtracts 3. But remember, you can always switch x and y and solve for y. And this way actually reveals a little bit more about the problem, because remember, when you take the square root of something, you have to put plus or minus in front of it. You don't have to put plus or minus on both sides though, because that's just redundant. It's like we're already taking care of the positive and negative case, so you don't have to put that on both sides. And now I just have to subtract 3 from both sides. So even though you can kind of think through it this way, that'll work for simpler functions, it's always better to just do it algebraically. So if you graph both functions, you can see the original was a parabola that was moved left 3, so the vertex is at negative 3, 0. But you can see the inverse is formed by the top half being the square root graph and the bottom being the negative square root graph. So we have to restrict the domain of the original function so that the inverse is also a function. So if I just wanted to keep the left side, that would be the x values that are less than or equal to negative 3. And if I reflected that side over the line y equals x, that would give me the bottom side here. That means f inverse of x would be the negative square root of x minus 3. If I just wanted to keep the right side of the original function, that would reflect over the line y equals x and give me the top side of the square root graph here, which would make the inverse of f of x be the square root of x plus 3. So it's the positive side. The next example says find the inverse of the square root graph, and it says where x is greater than or equal to 2. And they're just putting that there because we can't have x values that are less than 2, because if I plugged in like 1 here, well, 1 minus 2 is negative 1, and the square root of that is I, and I can't graph that on the xy coordinate plane. So just like last time, I'll switch this to a y, switch x and y, and then solve for y. Now the square root is already in the problem, so I don't have to have a plus or minus in front of it. They're telling me it's already just the positive side. So when I square both sides, I just get x squared equals y minus 2, and then I just have to add 2 to both sides. So I get x squared plus 2 equals y, which means the inverse of f is just a parabola that's been moved up 2. But that doesn't seem quite right, because the original function just had one branch going up, and now we're saying that the inverse has 2 branches, one going left and one going right. So I don't have to worry about the original function, that's just what it is. But with the inverse function, I have to restrict its domain. This top branch here would correspond to just the right side of the parabola. That's because the domain and the range of the original function was this, and when we switch the x and the y, that's like switching the domain and the range. So here the range was y values greater than or equal to 0. That means here the domain should be x values that are greater than or equal to 0. Since the domain was x values greater than or equal to 2, the range of the inverse should be y values that are greater than or equal to 2. So here, where I wrote the inverse of f of x, I have to add on to it. I have to say that it's the function x squared plus 2, but only where x is greater than or equal to 0. Just like they had a little addition to their function, we have a little addition to our function. And that should be enough to get us going with inverse functions.